not contain the information of what I just learned. 1 second after this point in time, I get a big order. My system will not react to that order until an entire T day. That's when it's going to react, right? Now what happens? It reacts and places an order, but you agree it still has to wait for the lead time? So here's what I want you to understand. The risk interval that you have to use safety stock for in a QR policy is only the lead time. You are going to need safety stock to protect against the uncertainty and demand during the lead time. The risk interval in a TTI policy is a full review period plus the lead time, so you're going to need the safety stock required to capture the uncertainty in T plus LT instead of just LT. That's where the inefficiency occurs. I need more safety stock in this system than I do in this system because I've got to protect against a longer period of time and more uncertainty in this system. It is an absolute mathematical fact. A TTI policy will always require more inventory to achieve the same service level than a QR policy. Yep?
Why can't we think in this lines like, how can I strategize to minimize the lead time?
Well, okay, so I have no problem. The questions you're asking are good ones, but you're not changing the nature of the policy. No, hang on, let me just say, you're not changing the nature of the two systems. You're saying, what can I do to change the parameters that are deriving those systems?
Yeah, I mean,
so, but if you change the lead time, you're changing both of them, okay? If you change the review period, you're changing the review period. So you can change those, and that's fine. But I'm just talking about for a given set of data, how do you calculate?
like when we went to Dallas and the Toyota, like the lead time, like they were talking about inventory systems where the partners are also part of the conveyor. Right in there. There's no lead time. I want this, we have. Is that the way to think it is just in time?
So if I'm trying to think how to answer this. I fully agree with you. You're kind of saying, but what about this? And I go, well, that's exactly true. But right now we're talking about, given that, what do we do? So whether your lead time is 49 days because you're getting it from China, or whether your lead time is 3 hours because Toyota set up the thing right in the middle, it doesn't change the fact that you still have to figure out these calculations. So I agree with you. You're giving me arguments about what we can do to change the lead time. Or you're giving me arguments about what to do about the service level. And I agree with you on that. I'm just saying, for a given lead time, for a given service level, this is how you set up inventory policies. Okay? Yeah.
Is the period fixed all the time? Like let's say if there is more demand versus no demand at all.
So you're asking another good question, just exactly like this. Can you make variants of these systems? Certainly you can, okay? So certainly, you don't have to follow the pure TTI policy. You can follow a modified TTI policy. Like, for example, anytime I see an order bigger than this, ask for human intervention to see whether I really want to wait until the next lead time to get. But I'm showing you the two foundational policies upon all of which the variants are based, okay? So stick with me on this. If you don't like these variants, that's fine, we can change them. But these are the foundations, and anything else is based upon this. I am never going to get through this.
We're trying to get you to take it off the exam.
What was your question? I forgot your damn question.
Okay. So once we have a last case at continuous time, if there's like a system monitoring inventory, and you have a safe what's the access level, the safety level, wouldn't the system just automatically trigger something?
No. Okay, I'm going to keep on going. I don't know how to answer your question because that safety stock is an outcome. You're not making. You only put two things into your computer program. You put Q equals this and R equals this. That's what you put into your computer program, okay? No. You put Q equals this and R equals this.
SS is an outcome.
That's exactly right. SS is an outcome. And all that happened is your stupid little dumb computer system said, oh, look, I did R. I'm going to place an order. I'll place an order for Q. And it does it and it keeps on going. Safety stock is an outcome of what happened to happen during that time. We'll have to take it offline, okay? All right.
Let's move on. The views are the same in here, but I'm imagining this formula is handled differently, correct? Because the risk
If
is
we
obviously
ever
no risk.
get to the fucking formula.
I'm right.
All right, so, all right, we ready? Okay, but I know, all right, but I do want you to understand something, all right, conceptually, because the math is easy, guys, once we get to the math, I swear to you, you're gonna go, oh, that's easy, okay, so here, I do want you to understand something. Here's a mathematical fact. You set up a system with a QR policy, and when you run that over the course of the year, your average cost of running the inventory policy for the QR policy, they are going to be less than the TTI policy. Which leads to a fundamental question. Why the hell would you ever do a TTI policy then? In 2020, okay, maybe in 1914, okay? In 1914, you didn't have the infrastructure, it was a pain in the ass to do that. But in 2025, why wouldn't you always just do a QR policy?
Because if it's not, you may not capture the fact that you get a bulk discount if you're not ordering enough product on that.
No. I can absolutely guarantee we're gonna get a volume
Okay.
discount because we're gonna set Q to make damn sure we do.
But a better bulk one, hypothetically.
No, this is always gonna do better on bulk ordering than that is. So
Got it,
that's
okay.
absolutely gonna be better. So a different question. Here's where this came up. I was a dumb new professor. I was teaching my EMBA class, no, actually it was the MBA class. We went down to San Antonio and visited HEB because I think Sean today has since retired, but Sean became the president of HEB, and he had graduated from our program. He took us down there, and he was running all the distribution and warehouse stuff. And we took a bus down there and toured around the different distribution centers at HEB, and then went to some of their flagship stores. And I was in the. We're having a lecture after visiting all these, and I go, and of course, HEB follows a continuous review policy because they have lots of technology and everything. And then Sean goes, well, actually, we don't. Okay? And so he started talking about this, and this is an interesting. I want you to think about this. What Sean said turns out to be more often the case than not. The problem with the QR policy is that it's asynchronous. You have no control over when orders are placed. Orders are placed when you hit that reorder point. There's no decision in a pure QR policy. There's no decision. You hit the reorder point, you place an order. What if you have 20,000 SKUs, and those 20,000 SKUs come from 500 suppliers? So one particular supplier may cover 1,000 of your SKUs. Do you see how if you run a pure QR policy, you can make no agreement with that supplier? You say, look guys, you're gonna get the orders whenever you get the orders. We can't batch them for you, we can't do anything for you, because they're all asynchronous. The order occurs when the order occurs. It's kind of Coco's question, okay? I have no control over it. The order occurs when the order occurs because it hit the R, because that's what the system does. And he goes, we just found that too difficult to manage. And then for my PhD, one of my advisors wrote, now you have to laugh at it a little bit. He wrote one of the most famous inventory papers, but that's like saying, you know, I'm the Arnold Schwarzenegger of the goldfish gem or whatever. Okay, so I acknowledge that. Okay, but here's what he wrote. He wrote a paper called The Power of Two. And what he found out when he did this is he said, if you calculate TTI policies, and you know we're gonna learn to calculate eventually a T for each of these items. So we're gonna have 20,000 items, and we're gonna calculate the review period T that we should order each of them at to do the best we can. If you simply arrange them to the nearest power of 2, I would have had to go through and say, what's my opportunity cost of capital, what's my risk premium, what are the storage costs, loss, other things. We lump that all together, and my holding rate is 25%. 25% means for every $1 of average inventory that I hold for a year, I'm going to charge myself 25 cents. That is my holding cost. All right, got that? And then it looks like every time I place an order, it's $200. It doesn't matter, right? These are just numbers to illustrate an example. So how would y'all, if I told you we're trying to solve this equation with those numbers, you'd put it into Excel, wouldn't you? In fact, if you like Solver, you could put it into Excel and you could tell Solver to try all the different Q's and find the best one. If you don't like Solver, you could do it manually like I'm doing right here. I said, well, let's try a few of these Q's. What if I ordered 1 at a time, 5 at a time, 8 at a time, 10 at a time, 100 at a time, or 1200 at a time? Now, obviously, I really have to try all the numbers in between as well. So there's no guarantee that the lowest answer of the ones I tried is the lowest overall. That's why you'd use Solver. But in principle, let's just take a look at 10. What if I decided to order 10 at a time? Q is 10. So just put them in this equation. Annual demand is 1,200. Q is 10. 1,200 divided by 10 is 120 orders. That's what that 120 orders is. And I pay $200 for each order. So basically, that first term in the equation is 120 times 200 is 24,000 a year. So on average, I'm going to be spending 24,000 a year, $24,000 a year in ordering cost if I choose to order 10 at a time. Is that clear? That's just the first term of the equation if Q equals 10. What about the second term of the equation? Well, if Q is 10, that means a bunch of little triangles of height 10. What's the long run average? 10 by 2 or 5. So the average number of units is going to be 5. How much did I pay for each one, given that I ordered 10 at a time? Well, given that I ordered 10 at a time, I paid $140 for each. So I have average inventory of 5 multiplied by $140 a piece means the average dollar amount I have in inventory is dinky at $700. And I paid 25% of $700 or $175. So that's the second term of the equation. First term of the equation, 24,000. Second term of the equation, $175. How much did I pay for all the stuff I bought? Well, I bought 1,200 units. I bought them 10 at a time, so I paid $140. 1,200 times $140 is $168,000. So therefore, if I sum the first term plus the second term plus the third term, I end up at $192,175. And I can try different Qs and find out whichever the cheapest is, correct? Okay, that's all I did. Now, of the ones I tried, it looks like ordering 100 at a time makes more sense. Why? Because I'm paying kind of a lot in ordering cost, and my inventory cost is dinky. So I might as well have larger triangles, so I don't have to order as many times per year. And you can see the ordering cost went down to $2,400, but my inventory cost went up to $1,750. I was already getting my full volume discount, so that's the cheapest of the ones I tried. In principle, you have to try all the possible Qs, and the right Q to order is the one that gives you the lowest possible number. Now, I don't see anybody in here having a problem with this because you have unlimited time to take the exam. So you can set up your spreadsheet and do this, right? But obviously, we don't have to do it this way. I mean, calculus can save us a lot of time here under certain circumstances. I don't mean you have to apply calculus to this problem. I mean, we're going to apply calculus and get the simplified answer. That's what I mean, okay? So let's try this. That looks like a calculus problem. Take the derivative of this equation with respect to Q, set it equal to 0, and solve for it. Then take the second derivative to see whether it's a maximum, minimum, or an inflection point. But those of you who know and like calculus realize we got a problem, don't we? Because the problem is, you see that C of Q that's right there? That C of Q is this kind of a graph. Calculus hates discontinuous functions, okay? It means that you can't just solve it once and get a nice, beautiful answer. For those of you who really like math, again, it doesn't matter, but for those of you who really like math, the truth is that you can solve calculus problems with discontinuous functions. It's just tedious. You have to check over each interval, you have to check the endpoints and everything else. So, what I'd probably do if I wanted to do this one, and if you guys are good at Solver, I just set this problem up, and instead of trying different Qs, I just use Solver, solve it, you're good to go, okay? But there are circumstances where C isn't really a function of Q. Remember, C is a function of Q because we get volume discounts. So you have to ask yourself, why do we get volume discounts? Why does a manufacturer or a supplier give us volume discounts? Part of it is to guarantee that you order more, right? That's why you would do it. But part of it is to try to amortize the cost of the setup Right? Did I?
Yeah.
When did I do this?
No, you didn't go over in detail. You did not go
We've
over.
been over this.
No, not in detail. He just mentioned why he did it.
Okay,
So please
sorry.
continue.
I'm gonna continue. Okay, so that's the first time y'all said stop talking as opposed to talk more. Okay.
Shut up, Brett.
All right. So the bottom line on this is that it is very common in today's world that we're going to go and enter a negotiation with a supplier, and we're going to guarantee a minimum annual volume. And we're going to go ahead and say, and you know what, to cover your setup cost, I'd rather you just charge me to set up. And I'll guarantee you an annual volume, and let's just get a price and then we won't dick around with all this stuff. In those circumstances, C is not a function of Q, right? C just becomes a number that we've negotiated based on an annual volume, but they're probably going to charge us a setup cost every time they do so. So in that circumstance, this becomes easy, right? This term is now a constant C instead of C of Q, and this term is now a constant instead of C of Q. Yeah? Okay. So, did we take the derivative? I can't remember. Did we do this?
No.
No, come on. Everybody in here can remember at least part of this, okay? So we're going to take the derivative of A by Q times S with respect to Q. Does anybody remember how to do that?
It's been a long time.
Does anybody remember it? That's Q to the minus 1. So it becomes minus Q to the minus 2. It doesn't matter, guys. I just give me my fun. Give me my fun, okay? Give me my fun, okay? This becomes minus A over Q squared S, okay? All right. Now, easier. What is the derivative of Q over 2 times C times H with respect to Q? Okay, fine. Q goes away, okay? That's Q to the 1, so you take away 1, it becomes Q to the 0. Q goes away, and this becomes plus CH over 2. That's what happens to happen, okay? Whatever, I don't care. This is my 5 minutes of fun, okay? All right. Everybody, what's the derivative of A times C with respect to Q?
A times C.
With respect to Q. It's not, doesn't depend on Q. So what happens when you take the derivative of something it doesn't depend on? It becomes 0. Okay? Turns out that leads to the EOQ formula. So what do you actually have to remember? You don't have to remember a squat of what I just said. Okay? What you actually have to remember is this. In the event that there are no volume discounts, so C does not depend on Q. You don't have to do a spreadsheet and try all the different things. You don't have to do any of that. You can calculate the right Q straight with algebra. You can say the right Q is simply 2 times A times S divided by C times H squared. And now you've got the right Q without doing any spreadsheet or anything else. And that's what you're going to do if I don't give you volume discounts. If I do give you volume discounts, all right, which I might, if I do, here's how I will do it. I will say, suppose you only have two choices. Q equals 10,000 or Q equals 50,000. Those are the only choices you have. Calculate this equation twice. Once when Q equals 10,000 and once when Q equals 50,000, and pick whichever one gives you the lowest cost. That's the right Q. Okay? That's all I'm going to do. It's as simple as that. Cool. We clear? Yep. I'm going to do an example in just a second. So now, what we've got, in fact, let's do a cheat sheet. I'm going to do a cheat sheet right here to show you all how easy this is. So this is what you're going to write down on your cheat sheet. Oh, I did not. God damn it.
Wait, you did not what?
Start recording.
Was it just this break or was it like way
No,
prior?
right from the beginning. Alright, fine, I'll go find an old video and post it so you guys can do it, okay?
Start recording now.
I did, but that's not gonna do any good, alright? Alright.
Was that up there to remind you something?
Y'all,
I didn't know if they were
Lance. Remind me.
I thought you told
You
me
fell
to
down on the
start
job.
recording. I'm not even.
Alright, fine, whatever, okay, so here, no.
Okay, come on.
All right, QR policy. Here's what we found so far. In order to find Q, all right, it's as simple as this. Volume discounts. If yes, then solve that equation. Total cost of the cycle stock as a function of Q equals A by Q times S plus Q by 2 times C of Q times H plus A times C of Q. So you have to use that whole equation if the answer is yes. If the answer there are no volume discounts, you can go directly to the EOQ, and the proper Q is square root of 2 times A times S over C times H. Okay?
Okay.
All right. That is as simple as it can possibly be. So I don't think you're going to have any problem. Now, what's the next thing? All right, what's the next thing? The next thing is now we got to figure out what R should be. All right, we got. All right, we're going to find out what R should be. Now, I don't need all these slides because we spend all of our time talking about this slide. There's the Q, that's that same drawing of the distribution up there, right? That describes how much demand we're going to expect. I drew it as a normal distribution there, I drew it as something other than a normal distribution up there. We have our reorder point that we've got to establish. That's the R up there, the reorder point. All the area to the left of the R here is the service level we're talking about, and all of the area to the right of the R is the probability of running out of stock. So it's the same exact picture right there, okay? So, we're just trying to figure out what R should be. We're going to use the central limit theorem. Now, we did go over this in Saturday morning in Dallas, okay? So let's remember what the central limit theorem says. It says, let's just try this. Our ultimate objective is to get figure out what that curve that describes the lead time demand is. That's our ultimate objective. Remember, this U is the lead time demand. Now, in principle, for Eric's class, we would go and do an uncertainty mapping like he did. I'm sure lead time would be in there, daily demand would be in there, the ability of the manufacturer to supply it. Maybe there's some risk that the supply chain breaks down and stuff like that. In principle, we could use what Eric talked about to generate this curve, correct? In principle. Now, in practice, you got to be able to do it for my class. And I'm not expecting that you go use at risk and do all the things that Eric did. So I'm going to simplify. Those of you who want more complication in terms of what that curve is supposed to look like, happy to talk with you about it, but for this purposes of this class, we're going to make a simplification just so we understand how it's going. We're going to say in our nice little world, the lead time is constant, so there's no variation in lead time, and the only source of uncertainty is the daily demand. That's what we're going to say in this class, okay? So I want you to think about this. The lead time demand is what? All right? Well, can I write this? Can I write, well, there's day one, and I don't know what day one's demand happens to be. It's a random variable, it has some mean, has some standard deviation. But if I can describe what day one's demand is, and I can describe what day two's demand is, all the way up to I can describe the lead time demand, is that a fair statement? I go in the future, I get in a time machine, and I say, what was the lead time demand? And I say, well, the lead time demand was however much demand was the first day after I placed my order, plus whatever it was the second day, plus whatever it was the third day, all the way up till whatever it was the last day before it arrived. Is that a fair statement? So, posterior, getting into the future and looking back, I can say the actual lead time demand was the sum of each of those days after I placed the order. priori, before the fact, I don't know what that is. After the fact, I can look and see what the number was, right? But before the fact, I don't know what that number is. But you know what? What if I knew the mean and the standard deviation? So I knew enough about each day to know its mean and its standard deviation. Okay, let's just assume that I did that. Do you agree that this is now just the central limit theorem? I am summing up, if the lead time is 16 days, and I know a typical day sells 100 on average and a standard deviation of 20, can't I just say that 16 days of demand summed up in a central limit theorem? Remember what the central limit theorem says? First thing is you get a normal, no matter what each day looks like. Second thing you get is the mean is the sum of the means. And remember, the third thing you get is the standard deviation is the square root of the sum of the standard deviation squared. Do you remember that from our Saturday morning discussions? What the central limit theorem always tells you. Go back and look at the video if not. Okay, so that's what the central limit theorem says. Okay, and we're just going to apply that here. If you can figure out what the mean and standard deviation of each of those days are, then we're done. This becomes trivial. Now, I might give you daily demand distribution. Okay? I might give you daily demand distribution, and I'm just going to say, well, the mean daily demand is 100, and the standard deviation of daily demand is 20. I could do that, couldn't I? Just give you the information. What else could I do? I could give you an estimate of daily sales. How would I do that? I would say A equals M equals B equals, and then I would say the mean is A plus 4M plus B divided by 6, and the standard deviation is B minus A divided by 6, okay? Either way, it's the same thing. In both cases, I'm telling you what one day of demand looks like. I am now applying the central limit theorem, knowing what the mean and standard deviation of each of those days is, and then with the central limit theorem, here's what it tells me. It says, my lead time demand U, it's the sum of those random variables, is distributed as, first thing is, it's normal. That's the first thing it tells us. It's normal. No matter what they are, it's normal. Remember my die example? Even though one die is a uniform distribution, if I throw 10 dies, it's between 10 and 60, and it's a normal distribution. So it's normal. What's the mean? What's the average of this thing? Well, it's the sum of each of the means, right? So this right here is mean of day 1 plus mean of day 2 plus all the way up to the mean of whatever the lead time demand is. If they're all the same, it's just going to be like if every day is 100. If we had this and the lead time were 16 days, then it's 100 plus 100 plus 100 16 times. So the mean is just 1600. Okay, and then remember the standard deviation. Okay, is equal to the square root of the sum of all the standard deviations squared. So let's just write that over there and do an example. Because right now you're going, oh shit, I was talking about this like 1 hour left in my first the end of the semester. Okay, let's just write this. It is no different than what we've done in class multiple times. All right, here's you. What do I want to know? First thing I need to know is I need to know daily demand. Okay, that's what I need, daily demand. And there's two ways I can get it. I can give you mean of daily demand and standard deviation of daily demand directly. Okay, I can give it to you directly. The mean of daily demand is 100. That standard deviation of daily demand is 20. Or I can give it to you as A, M, and B, but that's easy because then we just say the mean of daily demand is A plus 4M plus B divided by 6, and the standard deviation of daily demand is B minus A over 6. It doesn't matter which way I give it to you. You've now gotten the daily demand information. You know the lead time. you now know the lead time demand is gonna be equal to 1 day's demand plus the next day's demand, all the way up to the lead time demand. You now know from the central limit theorem that that means this uncertainty curve, that in principle could be more complicated because there's more sources of uncertainty. We're only including one source of uncertainty, which is daily demand. It's gonna have the properties of being a normal distribution. Its mean is equal to the sum of the mean of daily demand, so it's gonna be basically lead time times mean daily demand, and the standard deviation is gonna be the square root of lead time times the standard deviation of daily demand. That's what's gonna happen. We have our pretty little drawing. This is U, this thing right here. We have a distribution that describes how much we think we're gonna sell. We're only looking at the one source of uncertainty. In principle, it could be more complicated. We know the mean of this sucker, don't we? We just calculated the mean is the lead time times the daily demand. All right? We know the standard deviation of this sucker. It's the square root of the lead times the standard deviation of daily demand. Now we know the picture of the purple curve. What are we trying to do? We're trying to set our reorder point. So we set our reorder point here. Here's our reorder point. And we set our reorder point so that this area right here is the service level. Do you agree that's the same thing we talked about at the beginning there? So we just have to mechanically do this, right? So if I tell you the service level and that's a normal distribution, do y'all remember how to do that? Remember norm M and norm dist? Did you use that in stats or in Eric's class? If you don't remember it from Excel, in this particular case, here's the way you can look at it. In principle, the reorder point is equal to the average that you think you're going to sell plus the average safety stock that you need, okay? But if you want to use Excel, R equals norm inverse, where the mean is the mean you just calculated, the standard deviation is the standard deviation you calculated. Is for norm inverse, is it probability first? Can y'all check, or somebody look on Excel real quick? It might be probability first. Okay, let's just do this. Probability.
Probability.
Is it probability, then mean, then standard deviation? Okay, gotcha. Okay. So Excel will give you the probability, it'll give you the number that gives a particular probability to the level. So you're going to put whatever service level probability you want, whatever the mean is of the distribution, which is U bar, and whatever the standard deviation is of this. And now you got it, you're done. So, let's do it. Hang on, we're going to do it now. No smart aleck comments. Okay, here we go. We're going to make up an example, but I'll show you the TTI, we'll be fine. And basically, it's called a QR policy because Q is the order quantity. So this is how many you're going to order anytime you place an order. And R equals the reorder point. This is when you reorder. And here's how it works. I'm going to set my reorder point, R, whatever it happens to be. Now, this drawing is not the same as this drawing. This drawing is a probability drawing. It's talking about the relationship between how many you think you're going to sell versus where you set the reorder point. But that reorder point is this line right here. When my inventory drops to the reorder point, I place an order. So what happens in a QR policy? Well, the black line is going to represent the amount of inventory I have. So let's say I started up here, higher than my reorder point. in that case, what it looks like my order point is 15,400. So let's say I'm at 40,000 of these bumper plates. What happens over time? Well, the amount of those bumper plates declines. Why am I drawing it squiggly? Because it's stochastic, right? It's not a straight line, it's a squiggly line because I sell more some days, less other days, and stuff like that. So it's just a squiggly line. But do you agree, at some point in time, the amount of inventory I have in the warehouse is gonna hit that reorder point that I've established, and I'll know that point instantly because I have a continuous review policy. What do I do? Well, in the QR policy, since I can react instantaneously, at this point, I order exactly Q units. So at that point in time, I order Q units. So I get on the phone, do it electronically, whatever it is I do. Now what happens? That starts a race, doesn't it? I gotta wait the lead time, don't I? It starts a race. So let's start the clock on the race. So the race starts, a lead time occurs, and then some lead time later, my order arrives, correct? Let's draw the optimistic, I gotta do this. Let's draw the optimistic picture here. I place an order, I set my reorder point appropriately, and I didn't run out of stock. So what's gonna happen? This is gonna continue going down, but if I didn't run out of stock, that means I didn't quite hit 0 before my lead time elapsed, correct? And then this pops up, and it continues again. Do you agree the height of this bopping up is the Q, because that's how many you order? And then we continue on and do it again. Now sometimes we're gonna run out, it's gonna hit bottom. When we get our Q, we don't get as far above the R. Sometimes maybe we don't have much demand, so it doesn't get as low, it gets higher, so when we get our Q, we get higher. But do you see how this just continually runs over time? And we're gonna give I wanna give some labels here. Okay, these are the typical labels. LT is lead time, I'm gonna write them all over here. All right, do you agree how far we drop is governed by how many we sell while we're waiting? Do you agree that's the same thing we were trying to picture over here? So that's the exact same U over here. So the lead time demand is however many we happen to have sold during that lead time. Now that U is a random variable. That U is not always the same number. That U varies. Why? Because there, I got a picture of U. It's varied. Sometimes it's a lot less than 14,000. Sometimes it's a lot more than 14,000. Okay? In this particular picture, the lead time demand was less than the reorder point, so I did not run out of stock. We call this down here the safety stock. The safety stock is how much we had above 0. That is the amount that we had on hand when our order arrived. Safety stock can sometimes be 0, right? If we run all the way out of stock, we could have no safety stock. In fact, we had that one. And then the order arrives and it goes up. Is everybody cool with that? Okay, so let's write U is the lead time demand. S is the safety stock, MS is the safety stock, and LT is the lead time.
I'm sorry, can you say that one? You said the safety stock, you said it's the amount above 0, but then you said something.
Sure. Do you see in this picture, this particular time that we placed an order, I didn't run out of stock because that didn't hit 0. So I would say during that particular order cycle, we had safety stock, right? If in the next one, let's just do another one. If in the next one, it comes down, okay, we place our order for Q. Our lead time goes. But let's imagine that we got lots of demand during this period. and it actually hit 0 and was 0 until it got to the next stage right there. In that particular case, there would have been no safety stock because we hit all the way down to 0. Yep.
I'm having trouble understanding why is your point constant?
Because, tell me why it wouldn't be constant.
Well, because of the variability, because of the, with time.
Hang on. We're gonna take care of variability with the purple curve. So the purple curve is what's gonna tell us the variability in demand, the variability in lead time, and everything else. That's how we're gonna capture variability. Once we know the variability, we have a distribution that describes it. Now, we've got to pick an appropriate point in that distribution. That appropriate point simply becomes nu standard call. So once you've captured the variability in the distribution, the R is the number that balances those costs.
Not the axis.
I guess your assumption is that demand is going to be constant.
It's not that demand is constant. Demand has uncertainty associated with it. It's that demand is steady state. Okay?
Demand steady state, that's fine.
How about this?
It doesn't
Demand
change.
is stationary.
Got it.
Okay? Now, maybe this is what Shree's talking about. Suppose during half the year you have really high demand, and the other half the year you have really low demand. You're going to calculate two R's. The R that's appropriate for the uncertainty that occurs during the high demand, and the R that's appropriate when it's in the low demand. If that's what you meant, then that's correct. Now, we could take that a step further. I don't think this is the right direction, but we could have AI, big data and stuff. We could be constantly changing R. We could have a data analysis program that's looking at leading indicators and looking at our past demand data, maybe getting updates from our supplier in terms of if we were to place an order now, how long would the lead time be? If we were to place an order tomorrow, how long would the lead time be? We could be gathering this data constantly and constantly shifting what we think our picture of this purple distribution is and constantly reassessing what the R needs to be. We could do that.
Yeah.
And I'm saying there are systems that are trying to do that. Mostly people don't like them. And the reason people don't like them is they're unpredictable, they're unstable. And there's another reason I'm going to give you in a minute. But yes, we can absolutely do what you're talking
But you
about.
can do it with Overwatch, right? Obviously,
Right.
human intervention and changes.
I'm granting you guys that. You can do that, okay? Before you do any of that, we're going to first have to do it in a stationary process. And then we can change these things as we need to, okay? Yep.
But when you keep changing it, like you're also assuming your suppliers and the whole supply chain will also have like variability changing or adaptability to your different orders.
You're making that in.
I think what y'all constantly are asking me good questions about is this. You're telling me different ways that uncertainty can arise. I am telling you I agree with that, and in principle and inventory, where you're capturing that is in the purple curve. The purple curve is what's capturing your uncertainty. You tell me you have differential lead times. You have suppliers that sometimes are going to be shut down for weeks. You tell me that demand can spike during some times and not during other times. I'm going to say all of that is fine. The way what you're telling me is the uncertainty of how many that I think I'm going to sell while I'm waiting for that order to arrive is governed by those criteria. So there's no problem with what we're talking about here. You guys are wanting to argue the things that go into purple, and I keep on saying, fine, put them in purple. I got no problem, okay? It's not that R has the uncertainty. R is a number that is derived from the purple that has the uncertainty. Is that clear? Okay, yep.
The second line,
Yep.
stopping as one.
There's no safety stock here. The safety stock is at the end of the lead time, when your order arrives, did you have any still in stock? In this case, you had some in stock. In this case, you ran out of stock, so there's no safety stock. Because you don't know. So no, that's the whole, you don't know, right? That's the uncertainty, right? So I thought, okay, remember this, guys.
Ordered at the exact same
Right,
time.
not time, at the same inventory, same arm. No, interesting. Okay, so. So I love this. No, I love this because what, you're forcing me to try to explain kind of where the sources of uncertainty are. I like that. Eric will like this, right? He's all big on sources of uncertainty. If there was no uncertainty, if the lead time was always the same and daily demand was always the same, then we would know exactly when to order every single time, wouldn't we? If we sold exactly 1,000 every day and our lead time was exactly 14 days, then we can let our inventory get down to exactly 14,000. We can place our order and we're never going to run out of stock because there's no uncertainty, correct? Now add uncertainty in there. What are the sources of uncertainty? Varying lead time, right? Varying demand. Maybe the company we're ordering it from can't even meet my full demand, so they only ship a partial order, whatever. There's all sorts of things that lead to uncertainty. And so what we're doing is just trying to add a little bit of safety stock to protect us against all of those sources of uncertainty. We have to capture that uncertainty somewhere. Where are we capturing that uncertainty? In the picture that says, based on all of the uncertainties, here's the range of how many sales we might be exposed to while we're waiting for our order. So it's the purple line that contains all the uncertainty. R is a given, guys. Once you tell me what service level you want, and you express your uncertainty into the safety stock. In both cases, the safety stock was 1,400. In both cases, my rule of thumb said, I want to keep 10% of my average demand in safety stock. Or if you will, I want to keep, a day and a half worth of demand, or however you want to express it. You've expressed it based on average demand. The problem is, the exact same safety stock in the second picture leads to a very different outcome than the exact same safety stock in the first picture. That's why you can't protect against risk by specifying percentages of mean. People do it all the time, it's just wrong, okay? Yeah.
So that is where I'm tipping up in, what we do in the system is we have actually three inputs. One is inventory days of supply.
Okay, that's fine.
How many days you can survive
That's
if
fine.
the shipment is late.
That's fine.
The second one is the average variability per day.
Okay, I don't like that particular term, but at least you're trying to capture variability. So if you're trying to capture variability, I'm more happy than if you're not.
And the third one that is referred as buffer stock.
Okay?
If something happens and the whole shipment is lost.
Right. So the third one we'll set aside, we're not talking about that right now. The first two that you talked about are what we're talking about. Because you're tracking variability and that's influencing your answer, it's better than not tracking variability. I'm just going to teach you the way you ought to do it, okay? You want to do it somewhere else, that's fine. But I'm going to teach you how you ought to do it. Yeah, David.
Professor, when you change the metric
Oh, I'm a
from
professor now, okay.
so for units, right? We're talking about volume there, but if you change it to days of supply, would that
It doesn't.
get rid of the variability
It
and
does not.
distribution?
You've got to express, it doesn't matter. I don't care whether it's units or days of supply.
Yeah.
You've got to express variability. If you don't express variability, you're fundamentally doing it wrong. But we do it all the time, okay? So I just spent this week, okay, working with commercial folks at ExxonMobil, right? And we're talking about this exact same kind of thing, about how do you protect against uncertainty in deals you're making with governments? And the problem is, even companies that have the resources of ExxonMobil say, well, if our capital obligation is $1.5 billion, then we like to keep about 10% kind of as a protection against that. And I'm going to say the same thing to them that I say to you. That's dumb, because 10% of $1.5 billion when you're pretty sure of it is a very different thing than 10% of $1.5 billion when you're not very sure. So just bear with me. Okay, let's keep on going. This is the hardest thing to get across. After this, it's just mechanics. Okay? Do you agree if I were to draw the green curve on this, so let's go ahead and try and draw it in the same scale. Okay? That, I didn't reach 100% till maybe all the way over here, but I'm gonna be reaching 100% much sooner here, and I'm reaching the average here. So this thing is gonna be very flat, and then it's gonna go up very quickly, and it's gonna reach 100% very quickly like that, right? So the S curve for a narrower distribution is a steeper S curve. The S curve for a fatter distribution is a shallower S curve. But they both mean the same thing. So this is 100%, this is 0%, and I set this to here. So if we look at what this thing is right here, let's just call this 90%, okay? You okay with that? That's roughly 90% right there. So the point being, your exact same rule of thumb, I want to keep 10% safety, leads to very different risk outcomes between the two. 10% safety on the left-hand curve gives you a 60% service level. 10% safety on the right-hand curve gives you a 90% service level. I'm saying you don't want it as a specification to me. I want it to reflect the actual probability that you're willing to live with that you run out of stock. That's what I want it to do. And that's what all of our discussion is about to be, is to figure that out. Do y'all happen to remember when we were doing this Saturday morning, remember I told you something about any arbitrary distribution. So this isn't necessarily a normal distribution. And I said, if you were trying to pick the right number here, whatever you want this number to be, and you're trying to figure out what it should be. And I said, there's a very simple but very elegant thing called the news vendor problem. It said, what you need to do is you need to figure out how bad is it if you guess too high versus how bad is it if you guess too low. Take that ratio and that will tell you the proper area. So let's look at it here. If you remember, this area right here is supposed to be the cost of underestimation over the cost of underestimation plus the cost of overestimation. Now let's apply this to that picture, okay? This to that picture, and let's use inventory words instead of just arbitrary words like this, okay? So, the area to the left of a number, well, that's the area to the left of this number. Well, that's exactly the service level. So what we're saying here is the area to the left of it is the service level, correct? All right? If we then apply the cost of underestimation over the cost of underestimation plus the cost of overestimation, let's turn that into inventory words. Cost of underestimation. What if I underestimate what demand is going to be?
Lost sales.
That means there's a stock out, right? You agree? There's a stock out. So lost sales is going to be part of the cost, but I'm just going to roughly call this cost of a stock out. Okay? Over the cost of a stock out plus, now what's the cost of overestimation? What if we overestimate what sales are going to be and we hold more inventory than we have? So it's going to be the cost of holding the extra inventory, right? Okay? Cost of a stock out over cost of stock out plus the cost of holding inventory. Extra inventory. So let's first of all test this logically and then let's go do the math. Okay? It's all formal in just a second. What if you had a problem? Let's go back to kind of what Diego was talking about a little bit, and Arjun said this, okay? Sometimes you have A, B, C items or whatever, or you have different kinds of items. So let's imagine you had an item that if you run out of that item, it's very painful for your company. I don't know, maybe it's a loss leader, maybe the most important customers want to buy the stuff, but just understand if you run out of that item, it's very painful. And it isn't all that expensive to hold a little bit extra. What is that going to tell us in that ratio there, what service level you should want? Well, if it's really important to your company, the cost of a stock out is very high, right? And if it's not that expensive to hold inventory, the bottom right is a very low term. It's not that expensive to hold inventory. That's going to be a very high service level. So that's going to tell you you need a high service level for that point, right? Just exactly like logic would tell you should have. On the other hand, what if What if you're selling Cheetos at the HEB store? And you have 6 ounce bags, 2 ounce bags, 8 ounce bags, 12 ounce bags. You got regular Cheetos, you got flaming hot Cheetos, you got freaking flaming hot Cheetos, you got all those other things, okay? And let's imagine, okay, that running out of any one of them isn't very bad because the products are substitutable. And yet holding a lot of inventory means you have to give lots of facings, which means you can't put some other items on the shelf that you want. Do you agree in that circumstance, that again, we're just using that ratio, the cost of a stock out is not particularly high, whereas the cost of holding extra inventory is fairly high. Do you agree that's going to push us towards a lower service level?
Yes.
So it passes the smell test, right? I'm telling you it's actually more precise than that. It's exact. If you can tell me, which you can't, but if you could tell me exactly what a stock out cost you, and you could tell me exactly what holding inventory cost you, I can tell you exactly what service level you should do. And that's what we're going to be working towards. Now, why don't we do it like this all the time? I mean, for the same reasons you guys were talking. You can probably get close enough, right? By saying, well, here are my A items. And my A items have this characteristic, so I want a really high service level, and a rule of thumb that says keep 20% extra will generally work for me. On these other ones, I don't need as high a service level, so a rule of thumb that says keep 5% extra will work for me. Yes, those are rules of thumb. They're fine as long as you know where they came from. But this is right. Are we cool? All right, so that was all necessary to now be able to do the math, okay? Because what I want to be able to do is I want to be able, with you guys, to find out what the right R is. I want to be able to find out what the right reorder point is. Actually, I haven't even talked about that yet. We're going to order some more of those stupid red bumper plates. We go through all of this analysis to find out when we're going to order more. Here's a question for you. Okay, fine. The system has told me we've gotten down to 15,400. It's time to place an order. How many of you order at a time? Little itty bitty amount? A whole bunch? How much should you order?
It just depends on
the amount.
bulk order pricing, shipping costs.
Okay, bulk order item, shipping costs, what were you gonna say? What if I get shitloads of volume discounts? What if that factory, every time they're about to make this, I don't know if y'all have ever seen how a factory would make these kinds of things, but they have these big, giant injection molds, right? And they have to rip down the other molds because there's somebody else's mold making something else. They gotta rip that down. They gotta get your molds. They gotta clean them all up. They gotta put mold release compound on them. They have to go find the center hubs because those things have a metal center hub that the bar goes through, okay? They gotta put those in, and then finally they can start making. So they might lose half a day of production to tear down the old setup and put up the new setup and everything. They're not gonna do that for free, right? So they're probably going to try to incentivize you to buy a lot at a time so that they can amortize that cost over a bigger volume, right? So if I start giving you big volume discounts, what direction is that going to push you with respect to how many you should order at a time?
Depends on the cost of holding the inventory relative to the value of the discount.
You're right, but I want you to shut up for right now. Okay? John's exactly right, but I want you to focus on the one side right now. Do you agree that's going to tend to push you towards ordering a lot at a time, right?
Yes.
But now, what's the problem with ordering a lot at a time, John?
You have to hold the inventory.
Right, okay? Because if you order, let's just suppose they give you, you know how much these things cost? Literally, probably $200 to the manufacturer, to the person who's selling it to you. When you buy really nice bumper plates, 25 kilo bumper plate, 55 pounds, I'll bet you're paying $450 for one bumper plate. Okay, they're very expensive. So let's say that that Road Fitness pays $200 for them. Okay. Let's suppose that if you order 1 million at a time from that factory, the factory gives you a great price of only $175 a piece. But if you order 10,000 at a time, the factory charges you $200 a piece. We could order 1 million at a time, right? That would save us a lot of money in terms of how much we pay for it. The problem is, we got a big ass pile of 1 million of these bumper plates. It's gonna take a very long time before we sell those things. So we gotta pay for the inventory. And so that's exactly what's gonna happen. When we're figuring out when to order, it's gonna basically be what service level do you want, which is basically gonna be how bad is a stock out versus how bad is it to hold inventory. On the other hand, when you're trying to figure out how many to order at a time, this is now gonna depend, well, do we get volume discounts or not? How expensive is it to hold the inventory? How expensive is it to ship it? Because maybe you get a good deal if you can put it in one container. But what if you order a bit more than one container, and so it's 1.25 containers? Chances are you're probably gonna have to use 2 containers, and so now it got a lot more expensive to ship. You see how all of these have to be considered when you're figuring this out?
Well, possibly a bad example, but other manufacturing other products, you know, there's when they replace the product, when it upgrades, you technology, things like that, so the cost of losing the product.
We're gonna capture all of these ideas in something called holding cost, okay? So let's do that. We got it? Lots of discussion. I always like that in this class. Okay, it's fine. So we did it because we're just trying to get on speaking terms with the ideas. Now we need to actually be able to do the ideas. And so let's do it step by step, okay? It's gonna turn out, all of those things we just talked about are gonna come into play. I would like to let me go through these and I'll give you your first break, okay? It's gonna turn out, I'll write up here. When we're trying to figure out how much we should order and when we should order, we're gonna have to consider these 4 kinds of costs. One kind of cost is called variable cost. You don't really have to write this down because it's up there. But basically, just think of the variable cost as the per unit cost, okay? The per unit cost. So it's right here in the per unit cost where volume discounts will show up. Okay, volume discounts will show up. And if you get differential per unit cost, depending on how many you order at a time, that's gonna affect our calculations. In fact, we're even gonna use a particular term. C makes sense because, right, C stands for cost. So C is our per unit cost. But unfortunately, we gotta be careful because C could be a function of Q. So when I go C of Q here, easy way to remember this is just think about how volume discounts would look if you graph them. Q is how many you order at a time. So let's make this axis Q, how many I order each time I place an order. Now, what tends to happen with your pricing, your cost? So it's the price they charge me, so it's my cost. What tends to happen? Well, if I don't order very many, so if my Q is low, do you agree I'm gonna pay some price? And then I finally get to, if I order more than 1,000 at a time, they give me a better price, okay? So up to 1,000, I pay this particular price, so this is C of Q. And then if I go past 1,000, I get a better, lower price, correct? And then there may be several tiers like this. There might be a break point if I order 1,000 at a time, 10,000 at a time, and 100,000 at a time, or something like that. Do you agree that that's what this looks like right here? It's just a series of curves like that. So if the math bothers you and I write C of Q, just realize in your mind, it's just exactly how volume discount works. The cost you're paying depends upon the Q that you're ordering at each time, C of Q. And we're gonna call that variable cost. Then we're gonna call something, it's called ordering cost. But what I'd like you to do for this ordering cost is think of this as a fixed cost. And it's the cost of an order regardless of the size of an order. So like, you know, sometimes maybe when you were a kid, you ordered shit from the back of the comic book and there was the shipping and handling fee. And so it doesn't matter how many of these things you order, there was a shipping and handling fee. Well, there's a lot of costs like that. If you order from overseas, you're probably gonna be modulo container, okay? So whatever it is you're ordering, if it's a reasonable amount of, you're not doing split orders or whatever, you're probably thinking about how many containers is this thing. And you get charged a fixed price per container. Doesn't matter what's in the container, you get charged a fixed price per container. Yeah, David.
I'm wondering if, will you include another what we call opportunity cost. And the reason why is, so
I think the answer
we
is
made,
yes.
we made really good buying decisions in 2023 and earlier this year because of the contango curve of our product costs.
So you were watching the container cost?
Yeah,
We're not gonna get to that.
Okay.
You can play that game, but we're not gonna do that in this one. Okay? All right.
Too advanced to make
Okay? Now, hang on.
Go hang out with John.
It's Gabriel. Gabriel, that's great.
That's so Gabriel.
All right, so here. Now, hang on with me. I wanna get through this and then y'all can have your break, okay? So, we have our ordering cost, it's fixed. It's a per order cost. Doesn't depend on the volume. Now, we're gonna have the same problem we did, remember, in fixed and variable cost when we talked about it before. What if you order more than one container's worth? Now you just went into another container. So this has to be around a nominal operating point. Our typical order consumes 2 containers, so we're gonna say, what does it cost for us for our typical order, right? That's just the way we're gonna do it. And here's what we're gonna do. Whereas we use C of Q to determine our cost, we're gonna use the term S to be our ordering cost. And here are the components we're gonna think about every time we do S. We may be charged a setup cost by our factory. Right, so that factory, when we order from them, and they have to lose half a day in production to get rid of the old molds and put our molds in there, they may say, every time you place an order, we're gonna charge you half a day's production, maybe that's $10,000. That doesn't depend on how many you order. If you order one, that's a really expensive one-parter there, right? Okay, so our S, which is gonna be our fixed ordering cost, is gonna be our setup cost, plus whatever our fixed shipping costs are. So again, if you order a container, usually the cost of the container doesn't depend on what's inside the container. If it's a full truckload, then it doesn't matter what's in the truckload, it's a full truckload. So there's a lot of shipping costs that are based on a per shipment rather than a per item, okay? There are other things we're gonna have to think of in here as we go through and do this, because this is going to be a fixed cost given that an order occurred. In fact, well, let's wait just a minute and we'll come back to it, because with tariffs and going through customs right now, we're gonna have pieces of both, okay? And so I wanna show you those in a minute. So, first thing we've got is we've got these, what our costs are, and it may depend on how many we order at a time. Then we also need to know our ordering cost, our fixed ordering cost. Then we've got the one that most companies know. Okay? Our holding cost. And, you know, the debate is, how do you specify a holding cost? What's the right way to do it? The industry has standardized on something called a holding rate. Okay? A holding rate. And so here's the way the industry has standardized. Okay? It basically says, I want you to calculate your average dollar amount that you're holding in inventory over the course of the year. Now your inventory may get high, may get low, may get high, may get low, so your inventory may be changing. I just want to know the average dollar amount you had in inventory over the course of the year. And that's what that is, average inventory in dollars. All of this will become clear once we do an example. And then we're going to multiply it by something called the holding rate H. So I dollars is my average dollars of inventory. And H is called the holding rate, and it is a percentage. And the way to think about the holding rate percentage is, think of it as like a discount rate, okay? So if you tell me, if we go through and calculate for Bill, Henniger, the guy who runs Bill, if we calculate for Bill and we find out that he has an average of $10 million tied up in this kind of plate. Sometimes it's more than 10, sometimes it's less than 10, but it's an average of 10. And we determine that his holding rate is 10%. He is going to charge himself 10% times that $10 million, or $1 million to hold that inventory. That's what a holding rate is. It's a percentage, or how much we charge ourselves per dollar of average inventory held for 1 year. Okay?
How do you determine what percentage?
We're about to do that, okay? All right, so here we go. So, our holding rate, I didn't say that. Our holding rate has pieces to it. So let's do some thought experiment real quick, okay? Turns out holding rate's not the problem. The problem's gonna be the stock cost, okay? Holding rate. All right, let's just do a thought experiment. I hold an average of $10 million of these bumper plates at any given time in my inventory. Obviously, it's sometimes higher than that, sometimes lower than that, it's going up and down. But if I calculate over the course of the year, I have an average of $10 million. Will you agree that at the very least, that's costing me the opportunity cost of capital for that year?
Yes.
So whatever the opportunity cost of capital is, at the very least, I have to cover that.
Well, it depends on the interface though.
Well, it's whatever the cost of capital is, okay? So now there's debate on this. All right, so this is going to be a percentage. Now, some people argue that for a company, the opportunity cost of capital is your WACC. You go out to the markets, you raise capital, however you raise it, some of that capital you have to tie up in inventory. Some people will argue that the opportunity cost of capital is your WACC. Other people will argue that actually you can think of this inventory money as operating revenue that you can't use, and if you could reduce it somehow, if you could lower it somehow and take that money, there are things you could invest in with that money that generate a higher rate of return than your WACC. Okay? Just understand there are huge debates over what this ought to be. I'm not going to resolve those debates. I'm just going to tell you there's an opportunity cost, and it ranges somewhere on the low side, the WACC, to the high side, whatever the marginal return rate of the next project you couldn't afford would be. Do y'all ever talk about that like that in finance? You know, like if you're a company and you have access to capital, and you use up all the capital that you have, and you had 100 projects, and you funded 50 of them based on their rate of return. The argument is any freed up capital from that company is not really your weighted average cost of capital. It's whatever the return would have been on that very next project that you couldn't fund because you didn't have access to capital. So there are debates over this. They can go lots of different ways. I'm just going to call it opportunity cost of capital. I saw a hand. Are we cool? Everybody okay? All right. Now what else? Remember in finance, whenever you're trying to figure out discount rate, you have your base discount rate, and then you might have a risk adjustment sitting on top of it, right? So you have your risk-free rate, and then you add to it your risk adjustment to get your total rate, correct? Yes. Same thing's true here. So this is just having $10 million tied up in inventory, just your opportunity cost of capital. But what if that's $10 million of Intel CPUs? And at the beginning of the year, there were $10 million of Intel CPUs. But then Intel releases their next generation CPU. The problem you have is that the value of the inventory might have just shrunk, right? You might have obsoleted some of that stuff. Broadly speaking, that's what we call the risk of capital in inventory. So we're going to have to catch that too. So we'll call this risk of capital, or often called obsolescence risk. Now, some things may not have much obsolescence risk. Some things may have a positive obsolescence risk. If you were sitting on $10 million of gold in the middle of last year, and now you've got $23 million of gold, that was a positive obsolescence risk right there, okay? So that could go up or down. In inventory, we're generally trying to look at the risk of loss, but you can go either way on this one.
Yep. Just a quick question on this part, because I was thinking through this earlier. So the Intel example you gave, right? They just released a new chip, that risk is very low at that point. Because they just released the new one, you purchase the bulk right up front, right? So as it goes in time, how do you adjust the risk based upon the likelihood that they're going to re-release one?
This is kind of your question here. There's a lot of stuff tied up in the holding rate, right? And you can, there's a lot of debate now that AI is going to mean we're going to have kind of constantly auto-adapting holding rates and auto-adapting things. For the purposes of this course, let's keep them fixed. But understand that in principle, you can look at existing data and future data, and you can alter these on the fly.
Because a lot of times you may not know the preview information of when new releases will come out. They'll announce it, of course, and then you're stuck on it. You're like, oh, I gotta get rid of this inventory. Yeah.
Fair enough. Just so you know, this is not making stuff up. Every company that does a serious effort of managing inventory knows what their inventory holding is. It's dead standard, okay? All right. What else? I'm almost there, guys. All right, he's got to hold those bumper plates in a warehouse somewhere. If he didn't have as much bumper plates, he wouldn't have as big a warehouse. His warehouse storage cost wouldn't be the same, right? So you got to capture the storage cost associated with that. Again, it may be, it may not be. If I'm storing diamonds and I've got to have a super expensive setup, it could be very significant. So it's just another concept that goes into the holding rate. And the final one is loss. So those of you who've ever managed inventory know that most any government anywhere around the world requires you to do a physical inventory at least once a year, and you have to write down your write-downs, okay? So there's a loss question here. Collectively, as you're gonna see when we do our example, we're gonna put all of those things together into a percentage, and that percentage is called the inventory holding rate, and that is what we charge ourselves for holding $1 of average inventory for a year. Nothing at all controversial about what I just said. Absolutely dead standard stuff. Yep.
You can calculate all of this at one point.
That's his point. It could change over time.
It could change next.
Absolutely. Yep, that's right.
So in the real world, like.
In the real world, you probably divide your items into things that you need to constantly be updating and others that you're okay with. And you'll probably be constantly updating some of them and a lot of them just not worrying about.
Which is this done through like some systems?
Sure, we can use systems. You're gonna be surprised at some of the outcomes here. We can use AI, adaptive systems, we can look at big data, we can do all sorts of projections about what the future is going to be, and we can attempt to construct a very adaptive inventory policy. You absolutely can do that. The trend is probably not that direction, because those tend to be fairly unstable, and we're afraid of giving up autonomy. So you're going to see, when we come back from break, that we actually more often than not use this other system that's dumber than this, but it just allows us to control things better, okay?
Be in control.
Yeah, it's a question of being in control versus having a really intelligent thing that whacks out something. All right, let me get done, and then you get your break. The last thing we have to do, I don't like, on the term up here, the traditional term in inventory is called backorder cost. I don't like that. I'm going to call it stock out. And the reason I'm going to call it stock out is because backorder implies that if you're out of stock, the customer is willing to wait. That is sometimes true, that is sometimes not true. I think the better generic term is stock out cost. A stock out may result in a back order, but a stock out may result in a lost sale. Okay, so I just want to use that instead. Now, in principle, all right, we're going to do exactly the same thing. In practice, we can't, but in principle, what we want to know is we want to know the total dollar of average numbers of stock outs per year, and we would like to multiply it by a stock out rate percentage. So in principles, if you could tell me my inventory policy is going to result in this dollar amount of stock outs each year, and I can calculate what the stock out percentage rate is, I could just multiply them together and get a stock out cost the same way I got a holding cost. In principle, that's correct. In practice, it's impossible to get this number. Okay? So let's think about this. The stock out dollar amount, okay? The average dollar of stock out per year. We could do that. I'm going to show you how to do that. We could say, what's the likelihood of a stock out? How many times are we going to be ordering in a year? And we could figure out the average dollar amount of stock out. So that part's not a problem. It would be very similar to the way we're going to do this one. The problem is this other one, this stock out percentage. So So imagine, that's not a 50, that's an SO, stock out percentage, okay? Imagine that we wanted to try and write it in the same way we did this holding rate. So let's call this a stock out rate. A stock out cost rate, and we'd like to know it in percentage. So we'd like to know, what does it cost us on average for 1 year to have $1 of stock out? All right, what would be the pieces? The same way we were writing the pieces for holding rate, the opportunity cost of capital, the obsolescence risk, the storage cost and loss. Well, let's think about it. Customers coming, they're gonna buy this red bumper plate. They're out of stock of the bumper plate. They're disappointed, but they're willing to wait. What did that cost us now? Can we call that goodwill? Okay, we didn't lose the sale because they're willing to wait.
They bash you.
Okay, so they'll bash you, they'll say you're out of stock or whatever. So let's say at least part of it is some loss of goodwill. Yep.
Is there an opportunity cost in there too?
That's what I'm lumping it all in there. It's the loss of goodwill, it's the opportunity cost that we didn't get our money now, we'll get it later, and all of those kinds of things, okay? That's the most minor of this. Let's suppose that it escalates and it's not just a loss of goodwill and they're a little pissed off. Let's say they don't buy this red bumper plate. Now it's a lost sale, right? So it's lost goodwill plus a lost sale, right? Possibility of a lost sale. We don't know what that probability is, but there's some possibility of a lost sale. You agree? But it can be even worse than this. What if they were going to buy a whole gym? They're going to buy the bar, they're going to buy 4 of these 25 kilogram bumper plates, 2 of the 35, 2 of the 25, 2 of the 10s, they were going to buy a blue can, they were going to buy some other stuff, okay? So let's call that lost related sales. It is, I totally agree. Okay, so hang on, so I'll show you how, this is our dilemma, and I'm going to show you how we're going to address this, okay? Do you agree there's lost related sales here? Now what's the worst thing that can happen?
Word of mouth.
Word of mouth, you've lost this customer forever, right? Because what's going to happen? If that customer doesn't buy the stuff from you, that customer, instead of going to Rogue, is going to go to whatever, Garage Gym. And they buy it at the Garage Gym. And now they were satisfied when they bought it at the Garage Gym store, so they never go back to your store. So you've lost this customer forever.
Well, you know they're friends.
Okay?
Also, you can have fines as well, depending on the industry.
Lost customer, plus lost fines, plus lost pissed off, plus all of that other kind of stuff, okay? Now, here's the big question. I have no idea. We are starting to work on this exact question right now, okay? It's one of our research topics. Can you use AI and big data? You know, you can map out a website, and you can look at the path of any particular customer going through the website. I think it's almost a decision tree, guys. You know, the different pages you can land on, and you can map it all out. Looks like the decision trees you did with Eric, and you can find the probabilities that customers go from link to link and do all that stuff. And there is research starting right now about the idea, can you use AI and big data to track what's happening, to try to infer what these are? I'm skeptical, okay, but then I'm skeptical of AI. So don't worry, I'm not going to pull a row on y'all, okay, but anyway.